All right, so I'm starting the recording. Um, First question I see from Carlos is the final on Monday, or is it take-home style? So I'll put that as a yes with a caveat. It's going to be on Monday, but I'm kind of going to do it a little bit take-home style. I'm not going to make it like overly huge. It's going to be what I think you will be able to take in 2 hours. I'm going to use kind of more of an honor series thing. So I'm going to open it up on Monday morning, and I will give you till, you know, like a window, maybe 6 hours or so, somewhere around there, to be able to get them done. And then 2 hours, if you're a normal person, you should finish it within 2 hours. And I will probably have to dock some amount of points. There are some people who have time extensions, so I'll let them take whatever that time extension is. But for fairness, I want to have it about the length of a normal time test. So it'll just be a little more on the kind of honor system to do it and to hand them in. So I might give a set time for you to pick them up and start the clock at that point. That probably is actually the easiest way that I can do the timing on this. So I'll probably start it at the regular time. I think we're at 9 a.m. So I'll probably release it at 9 a.m. And then from everybody who doesn't have a time accommodation, have it uploaded. I'm just not going to force you to use one of the Respondus browsers because I don't think that's conducive. I do allow you to use notes and stuff like that. All right, that from Carlos, that helps. I'll write all this down and put it in an announcement too. All right. The way this works, I stay here until everybody's questions are answered or 2 hours expires. So I have nothing that's really prepared per se because it's kind of what questions do you have? So probably the easiest way is to just, when you have a question, unmute yourself, ask the question, and I will answer it on my wonderful black or whiteboard behind me. I am now at your disposal.
Ask a question over one of the old homeworks.
Sure.
I don't know why I just couldn't get this one. It was the question that said, using K-maps for F, convert the following Boolean function from sum of products to a sum of products form to a simplified product of sums form. And then it was F of Y of W, X, Y, Z equals.
Let me see if I might be able to pull it up. Which homework is it from?
Homework 3, question 5.
Homework 3. Okay, so it's using the K-maps for F convert to a sum of products.
Mm-hmm.
Is that the question?
Yeah.
And the function is 0, 1, 2, 5, 8, 10, 13.
Yep.
Okay. So we first draw our, see what the variables are. W, X, Y, and Z. So again, this is kind of the order I put them in. Just I think
Mhm.
it makes it a lot easier when you go to write them. And let's see, our function, we've got sigma. So sigma tells you where the ones are. So 0 and 1, 2, but not 3, 4, 5, not 6 or 7, and then 8, 9, 10, 11, 12, 13. Okay, so if I copy my map correctly, that's what I should have. Okay, and then we want a product of sums form. Okay, so for product of sums form, we want to encircle the zeros. So I'm going to pick different colors. We'll do that one in black. We'll do that one is purple. Got a green here. And we'll do a blue across the line. Fair for the encirclement?
Yeah.
Okay. Now, let's see what we want. Let's start with probably one of the easiest ones that's here. The first one I did right down the middle.
Mm-hmm.
Right? Now, if I was encircling ones, this would be Y and Z.
Mm-hmm.
Right?
Oh, I forgot that I
But
have.
I'm encircling zeros. So since I'm encircling zeros, the ones are actually in not Y
Mm-hmm.
and not Z.
Okay.
So I have to do that one. Right? Not Y gives me these, and not Z will give me these, but I want both, so I'm not or them. And that leaves the zeros only where Y and Z are true.
Mm-hmm.
Does that make sense?
Yeah, I forgot that I have to invert like the.
Yeah, that's the one that always gets when you go to product of sums. And that's why product of sums isn't quite as popular as sum of products for a lot of design, just because you have to be a little more careful with it. It does allow you to implement with NOR gates, though, instead of NAND gates. So it does open up a different type of logic, which sometimes better fits the problem that you're dealing with.
Okay.
Do we want to do the rest, or do you feel good now that you realize what the problem was?
I think I feel good on that now.
Okay. So,
Mm-hmm. Also, I'm still kind of I still don't get like the I guess the main idea behind like the right hand side and left hand, or like the most significant bit and the least significant bit.
ah, um, so let's imagine we had, let's first do just, I'm presuming you mean when you're talking left and right hand side, you mean of a number.
Yeah.
Okay.
Because also I remember in the last lecture you did an example, or I'm not sure if it was the one before the last one.
Well, we sometimes do left hand side and right hand side of like an equal sign, or a non-blocking equal where we say, X and Y or Z or something like that, right?
Mm-hmm.
Should do it. Right. So this is for an equation where I'm doing an assignment. This is the left-hand side, and this is the right-hand side.
Okay.
Right? And this is the one being written to, and these are the ones that are being read.
Okay.
So it makes, left-hand side and right-hand side really just are left and right. And so you have to know the context. So in an equation, that's how we relate them. It's like when you're going through looking at, for instance, like Verilog stuff, anything on the right-hand side has to be red. So it should be part of the active triggers usually.
Okay.
You know, and since they're being read, these can be inputs, but that cannot be an input.
Okay.
Because you're writing to it. You can't write to an input.
Mm-hmm.
And writes can be outputs, right? But these cannot be outputs. Because you write to an output, you don't read from an output.
Okay.
Right? So in an equation, it's one thing. When it sounds like you're dealing with this number. So let me put down a number. What's that number in binary?
6.
Okay, so how do you know it's 6?
I added like the 4 and the 2.
Right, because this one is worth 1, and this one is worth 2, and this one's worth 4, and this is worth 8. We get these numbers from 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So of these digits, which digit is the most important one?
The largest one.
The largest, which is over here on the left. So this is our most significant bit because it's got the most value to it.
Okay.
Right? It's worth 8. This one is only worth 1. It is our least significant bit.
Okay.
And it's on the right. And this is a general convention all over the Western world. You know, I mean, this is not 125. Right? It's 521. So we often will write, or we pretty much always write the most significant bit on the left.
Okay.
When you go to Verilog, you get to number them yourselves. So you can say, for instance, 2 down to 0, which what that means is the bits are numbered 2, 1, 0.
Okay.
Right? So when I go to refer and we have to deal with these, like say I'm dealing with a state that has, say, 3 bits, right? I mean, I could call this the 2 bit, the 1 bit, and the 0 bit.
Mm-hmm.
Or I can call it the most significant bit, and this one the least significant bit, right? And this is the other bit, right?
Yeah.
We could also call this the second most significant or the second least significant.
Okay.
Right? So we can put those. It's just a way to give you a reference to which bit we're talking about.
Okay. Because another thing that I was confused about, I guess, because when you made a flip-flop, like schematic, and you worked through it with an example, I remember someone said something like, "Oh, it makes sense why the most significant bit is more important," or something like that, with regarding the flip-flop. But I was confused on that.
So a single flip-flop is only 1 bit.
Oh.
So when you're dealing with, least or most significant bits, there has to be multiple ones carrying in.
Okay.
I'm not sure which exact one you're talking on, so it's hard for me to make a specific comment. But there are some cases when you make registers, right? We will often, for like a serial register, we've got D to Q, D to Q, D to Q. Let me just do my 3-bit one I was just talking about. Right? We often will call this the most significant bit and the least significant bit. Because if I want to write in my number, like if I want to write the number 6, it would be 110.
Okay.
Right? And it's just, the only thing that's obvious about is by sticking that one on the left, it just makes it human readable.
Yeah.
Technically speaking, I could call that the most significant bit if I really wanted to. Right? Mm-hmm. There is a little debate over which way should you start and make the equations flow. And this becomes an issue later on when you get into computer architecture. And they call this big endian versus little endian. should the big end go first, or should the little end go first and the big end is on the last?
Okay.
Right? And technically speaking, you could do it whichever one you want as long as people know what you're doing.
Yeah.
Right? Then as long as people know what you're doing, they can account for that. They just have to know. So the argument between which one do you do now becomes kind of, an unimportant debate in the grand scheme of things. And so this is actually a reference back to the Lilliputians, right? In Gulliver's Travels, they had this big war over which end of an egg, hard-boiled egg, should you eat from, right? Should you open, like if you look at an egg, they're not really oval. One end is more pointy than the other. And, big end versus little end. It was kind of a joke of how important really is your war and how often do people get into big battles over insignificant things like which side of an egg do you want to eat. That's a fictional reference, but that actual reference was big Indian and little Indian was used in the area. So it's used here since there is a big end and a little end. And does the big end go on the left or does the little end go on the left? It became a kind of computer joke, and that's what we call it by.
Okay.
But yeah, if you do these, you've got that choice. When you go to parallel registers, now it's really, right, because they're in parallel, so there's no defined sequence to them. So if I have a parallel register going through, let's say like 4 of these, right? D to Q, D to Q. Okay. Do I make this the most significant bit or this? All right. There's nothing supernatural about which one of these, right? Because they're all coming in parallel now. Right? So it's kind of arbitrary. Now I could say the first one I hit is the most significant. That kind of fits, a human scheme that's in here, right? So if I wanted to, store the number, let's say 11, right? I could store, in this one I could store 1, 0, 1, 1, and that's the number 11, right? Making this the most significant bit. What's going in, but I got to pick that.
Yeah.
Right. I have to have some way of telling you which one it is. So I could label this as the MSB, in which case you now know that's the biggest number, and it goes down. And often, just for kindness, I'll call this the LSB. The other way I can let you know that is just numbering them, 0, 1, 2, 3, because then you can get the value by 2 to whatever that number is. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3.
Okay.
So you can pull them off. But putting the biggest one on top, right, that's an arbitrary convention. I could put the biggest one on the bottom. Again, big Indian, little Indian argument.
Yeah.
Right? And sometimes it makes sense to start from the small ones and work down because the small ones are changing the most. And if you look on a lot of the books drawings, they started with the small ones and cascaded down. Because if you need more digits, you add more. And it makes more sense to kind of add at the bottom. So there are times when you'll want to draw them from little to big, and sometimes when you'll want to draw them like I did here, big to little.
Okay.
So the point is there's no hard and fast convention. It is usually either big to little or little to big. We don't like some weird mixed convention. But between these two, all bets are off.
Okay.
Right? So the person giving you the problem has to specify. Or if I don't specify and I don't give you like the exact number, I tell you, draw me a thing. You're getting to choose the drawing. You can choose the way you draw it.
Okay.
So if I just tell you, hey, you have 4 registers and how would you build this, right? Then you get the option to choose which convention. You should pick one of the two. I really don't care which.
Okay.
Does that make sense?
Yeah.
Awesome. I belabel that one a little because it does actually become an issue on computers.
Okay.
like for instance, Intel likes little endian. So their computers are all little ends first in the address space. Yeah. But a lot of non, Windows machines, like the ARM processors, for instance, are all big endian.
Okay.
This kind of trade-off between machines, that are different. So when you switch from one to another, you get them. Linux tends to like big endian because it copies Unix, and most Windows ones are little endian because they're usually implemented on Intel machines, whereas Linux machines could be anywhere, so they have to pick a convention and be consistent. So there's a lot of these type of debates that go on, but when you switch files from a Linux machine to a Windows machine, for instance, you do have to be careful about the order of your bytes, and that plays out. So when you do get to computer architecture, or when you get to anything, the embedded systems class, microcontrollers, anything like that, just keep this in mind.
Okay.
Cool. Other questions? And welcome, Tyler. So just for your benefit, Tyler, for just entering, basically this is a Q&A session. You ask questions, I give answers. Other questions?
All right. So, like number 2 in the practice funnel, I know there were no errors as I went through it, but what if there was? How would you fix that, like in the ASCII characters?
Yeah. So when you're dealing with ASCII, so ASCII is always 7-bit. That's the basic ASCII. There's different forms of it. There's an extended ASCII that gives you 8 bits and allows a little more characters. But the basic ASCII code is 7 bits. And you'll see them kind of put in a table. Usually we do 4 bits down this side, and the first 3 bits go across. Right? So if you look at the last 2 columns, right, which are the numbers 6 and 7, you basically have the alphabet starting with A and going all your way down, eventually C. And then before it in 4 and 5, you have the little a going down all the way to little z. Same exact positions, right? That's going in. So for instance, we can look at this, and this capital A here is in position, right? So this starts 0, 1 as it goes down. So you can take them, and it's 6, 1, right? Gives you A, or 4, 1. So let's just say, for instance, I had 6, 1 was the particular letter A that I wanted. And so for 6, 1, I can, 6 is 1, 1, 0, and 1 is 0, 0, 0, 1. Just remembering how many bits for each. So if I were to count these, I have 1, 2, 3 ones inside the binary representation for it.
Right.
If I'm doing even parity, I don't want odd numbers, so I put an even number. I add an extra 1 to the beginning. Now I have 8 bits. That's a byte. That's a nice thing to transfer. And actually, I think I reversed this. I think this is the littles, and that's the caps. But yeah, doesn't matter for this part of it, right? So I've got, my letter A, I've now got this. Let's say an error happened. If I were to flip any bit inside here, right? If I flip a 0, I increase the number of ones. So I would go from 4 ones to 5 ones. If I were to flip one of the ones, it would go from 4 ones to 3 ones. So if I get an error, I'll either get 5 ones or I'll get 3 ones. If I get an odd number of ones, I know I have an error. Right? It doesn't tell you which one it is. It just tells you something's bad. And I can tell if it's 5, it was either the A and it's, increased up, or it could have been one of the nearby letters and it flipped a bit down. So I don't even know the original character from it. Okay? There's a number that could have contributed to it. So I have no easy solution to which one is the one that flipped. But I do know that it's wrong. It's impossible in even parity to have either a 3 or 5. But if I get this with no flips, I'll get a 4. And if I have 4 ones, I know it's even, so there's no error.
Okay.
Now, the way this would work in practical life is, let's say you get, a byte and it is odd and you're expecting even parity, right? Since you don't know what character it is, you can't actually put a value in. You can't correct it like you can with a Hamming code. Well, what you can do is it's a problem. So you can go back to the sender and say, sorry, what was that? It didn't come across right. And you just ask for a resend.
Okay.
And so, as things are being sent to me one at a time, I just check them as fast as they're coming in. And if there's ever an error, I say, resend, please. Because what they'll do is they'll send me a packet. I'll check them. If I get errors, I say resend. Right? If I get no errors, I go, thank you. I send it acknowledge, and it sends the next block.
Okay.
Does that make sense?
Yes, sir, it does. Thank you.
Yeah, so it's really only meant for that check thing. So if you get an odd number of ones on even parity, it's an error. And so when you have multiple bytes, you just go through on each byte. And if each one of the bytes is even, then you say it's no error and on you move.
Okay.
So on that particular one, I didn't flip anything.
Right.
So I just, I let that pass through. And so then you're able to you then can ignore the first bit of there, and the rest of it is just your ASCII code. Right? This one tells you your column, and this one tells you your row.
Okay. Okay. So if there had been an error in the problem, we wouldn't have been able to give the message, correct?
Yeah, if there was one error, one of the letters would be undecipherable.
Okay.
Right? And you don't know which one. Like if I had flipped one of the ones in the 6, right, and so that became a 4, that's still a legitimate character. It just now you don't know was it capital or small, for instance.
Okay.
Right? So when you receive it, if you received a 0 here and you go, oh, it's an error, right? There is a legit 0 column, so that 1 could be the flip. There is a legit 6 column, so that could have been a flip, right? There is a 5, so that could have been a flip, right? But instead of also 1, I could have been at 9, right? I could have been at 5, I could have been at 3, or I could have been at 0. All of those are legit characters.
Okay.
Right? So it actually leaves me with 7 possibilities, and I just don't know which one to pick between.
Okay, that makes sense. Thank you.
You're welcome. All right. Other questions?
I had a question over the Mealy and Moore. I remember one way to tell was like from one of the homework, from the last homework you gave us. It was like like for example, all the outputs were all like defined or like assigned inside each of the states. So like one way.
That's the whole definition.
Oh, okay, that's it.
More depend on state.
Okay.
Only. That's the only is really important for that one. And for Mealy, right, the outputs depend on state and inputs.
Okay.
That is the whole difference between the two.
Okay. Cool.
So if you think of more, you'll see like registers, and the registers, you know, will have some type of a logic function in here that will determine the output. But it's only coming from the registers. That's assigned it to more. For a Mealy, you might see like a register and some input coming in. And those ones go into some logic function to determine your output. That's a classic Mealy setup.
Okay.
That's going into it. When you're dealing with state diagrams, right? If you have the state, whatever the state name is, and then the output, right? You can easily tell that's a more because it's inside the state. You don't need to know what the inputs are. Whereas on a state, that's a Mealy machine, your inputs, well, the inputs on both are here and state is here. If you see a slash here and then the Y, now you know, okay, it's not, it depends on the input as well as the state. Therefore, this is a Mealy.
Okay.
But it really is the same definition everywhere.
Okay.
And the importance of this distinction is the fact this one is really safe because it comes from registers, so there's no glitches in them. But it's slower and it's bigger and all kinds of other stuff. So now you've got, you know, slowness and safety going on here, but danger and speed.
Okay.
Right? So there's things we like on both and things we don't like on both. So now you have to pick what you want.
Okay, sweet.
So one thing to often do is you usually put more machines on the boundaries. So things initially come in and they're synchronized. And you can sometimes get away with some Mealy machines internally to speed things up. And they're protected a little bit by the more machines that precede them. So if this input was an output of a more machine, that input would be really safe.
Okay.
So there are ways you could sometimes mix them to be able to achieve a purpose. They're good questions. Other questions? All right, we're back recording.
Do you mind going over that like trick for going for the Mux design? It's kind of like setting it up quicker.
Yeah, sure. So one of the basic ways I do Mux design, Mux design is usually done by grouping things into groups of two. So if you consider a truth table, so imagine I have whatever X, Y, and Z. And I'm considering that whatever here on the left is my most significant bit to my least significant bit. At least in terms of what's important for grouping, if nothing else. And I take advantage of this. So like when you consider the whole table, I've got 0, 0, but I'm not going to list X and Y on the second line. I'm only going to do it on the first. They are both 0 here, so I don't need to copy them. Then this is 0, 1, 0, 1. And obviously this is 0, 1 also. And then I've got 1, 0, 0, 1. And this is obviously 1, 0 still. and then 1, 1, 0, 1, and this is obviously 1, 1 also. Right? Now, you could list them. In a normal truth table, you would. The reason why I don't is because 0, 0 is the number 0. And 0, 1 is the number 1. 1, 0 is the number 2. And 1, 1 is the number 3. So this becomes the inputs to my mux. And what's determining these two is the address here, which is, right, X, Y, concatenated together. Right? So X and Y in that order tell me whether it's 0, 1, 2, or 3. So far, so good?
Yep.
All right. Now, I want to implement some function f. And whatever gets placed here, there are some options. It could be a 0, 0. It could be a 0, 1. It could be a 1, 0. It could be a 1, 1. It's the only two possibilities. Or sorry, the only four possibilities for this two-spot combo. But this is always 0. Right? So I could hook it to ground. This is always 1. So I could hook it to power. 0, 1 is the same as Z. And 1, 0 is the opposite of Z. So when I take my function f and I've broken them up into groups of 2, I'm going to be breaking them up into combos of either 0, Z, Z prime, or 1. So 1, 1, 1, 0, 0, 1, 0. Fair?
Yep.
All right. So I just come in here and I look at my combo. 1, 1. Oh, that's a 1. So input 0 gets a 1. Right? For location 1, 1, 0 is Z prime. Right? So I put a Z prime there. Which is as easy as just taking Z and running it into an inverter. My next one, address 2, 0, 1, is Z. So address 2, input a Z. And then address 3, I've got 0, 0, which is 0. The output is F. Right? That's the whole trick with mux design. This is the basic form of mux design, and it's fairly simple. So you notice if F has 8, I only need a 4-input mux to handle it.
Okay.
So you need, for basic mux design, you only need half.
Okay.
Now, technically speaking, if I wanted to, I could actually take a really gigantic mux that goes 0, 1, 2, 3, 4, 5, 6, 7. This takes 3 bits to address, and I can address of X, Y, and Z if I wanted to, right? And then I could just go in, 0 is the first line, so I could just go 1, right? 0, 0, 1, that's 1, that's the next line, 1. So I could do it one at a time, but this is like a huge waste. I'm twice as big. I just literally copy these down, right? 1, 1, 1, 0, 0, right? 1, 0, 0. I can plug them in. That is also F. Now, between these two, this is hugely more wasteful than this. This is why we like this version.
Mm-hmm.
Right? But technically speaking, you could do it. There's nothing wrong with it, other than it's just really wasteful.
Okay.
Right? Now, sometimes, if this isn't just a 0 or a 1, if you're explaining, if this was like a state, and then you were doing something at a state, then it might make more sense to do something like this, right? If instead of F being a 1, I said, or all the bits together for this one. And over here, I say, you got to do something else. So it would then make sense I could have each of those circuits running in and pick between the 8 different options you wanted.
Yeah.
that type of a functionality where you use this as a function code and then you have different circuits for it, you'll use in computer organization. This is how you're building ALU. Like you'll have a code that'll say addition, subtraction, do an and, do an or, right? You have all these different function codes, right? And this is what becomes, assembly or machine codes inside. So when people talk about assembly language, all they're doing is they're calling these basic function things. They just give word names for them in assembly language, and they use the actual function number codes inside machine language. But that's all it really is. Getting down to somebody did a mux separated out this way, and you're just breaking it out for the function codes.
Okay.
So you'll actually build that in comp.org. You'll build an ALU. Does mux design make sense?
Yeah. Thank you.
You're very welcome. Any other questions? All right, so a question, are JK flip-flops built the same as SR latches, but include a clock? So there is a subtle difference actually between a JK and an SR. If you remember for our JKs, we had basically 0 as a hold and 0, 1, 1, 0, 1, 1. And this was flip, and this was a reset, and this was a set. A flip-flop obviously has a clock, and it uses the edge of a clock, whereas a latch either has no clock or doesn't use an edge. It either uses the entire time the clock is high or the entire time the clock is low. So latches don't have an exact timing where flip-flops do. That's the whole difference between flip-flops and latches. SRs do hold, reset, and set, right? Because that's actually what set and reset mean. Right? So remember, there's two forms. I'll do the form where one means to actually do it. So you have the exact same code here. Hold is when neither one is set under that form. But if you remember, this was a disallowed state. And it was a disallowed state because you don't know what you're going to get. It doesn't do flip, it does something else. So we basically had this illegal state. So when we went to the edge trigger, we said, well, we could also put some logic in that will prevent this from ever happening and give us something else. Right? It'll prevent the problem here. Right? And so, to prevent this logic problem, we added extra logic that encoded this 1-1 to force it to do a flip. So it was redesigned. So there's an SR at the core that has a JK logic input and edge triggering to make it a JK flip-flop. That's basically the difference. If you remove the edge triggering, you could technically take all the logic you did and make a JK latch. Almost nobody ever does because JKs are designed to be very flexible, particularly for use when you're doing like Carnot maps and things of that sort. So we often want to make sure we have that edge triggering and stuff like that. So generally, think of this as the souped up version of this. So going from latch to flip-flop, you add the edge triggering, and going from SR to JK, you take an error and you make it an extra logic functional flip. Does that make sense? Awesome. Any other questions? So just as a general note, with regard to the final, don't really worry about latches. And latches are not fully synchronized, and so designs involving latches are much more complicated. It takes several weeks to explain all the rules with them, how to race conditions, and all kinds of other stuff like that. So I make that part of the advanced digital logic class, how to handle latches. They're faster, but they've got problems or potential problems. So it's another one of those speed danger trade-offs. But I don't think it's appropriate to do with the first course. So I introduced the flip-flops just because you can't build, I introduced the latches because you can't build a flip-flop without a latch, right? But once we've introduced the safety features to it, I'm going to ignore it until the advanced class, right? So we deal with the bigger, safer systems, and then we'll teach you to deal with the small, fancy ones if you decide to go on to advanced digital. Okay, other questions? All right, a question on the final, is it going to be in a take-home format? I commented about this at the beginning, but for those who entered later on, the final, my plan is to still have it be a 2-hour length, but rather than do like a lockdown browser and all that, I'm just going to do a honor code version. You're going to sign a thing that says you're doing this, honestly and whatever. And I'll release it at the start of the final block we have, which will be 9 o'clock. I will make it such that if you're basically studying it up on it, you should be safely finished within the 2 hours. If you have an accommodation that gives you extra time, either 1.5 or 2, you will be allowed that accommodation. So people without accommodations will hand them in at 11. People with 1.5 time accommodations will hand them in at noon, and people with 2 time accommodation will hand them in at 1. And I can just check the date stamp or the time stamp on it to make sure that's done. And I'll say a call out and things like that. But since I am allowing you to use, notes and stuff like that, I'm obviously not there watching, but the book really doesn't help you. So I'll have a thing where you sign and say, hey, look, I'm just going to use my notes. Those notes are very helpful. I'd suggest taking the notes from your the midterm, plus making more notes for the final. Those tend to be, kind of the better way to go with it. Something that's you've written up, you kind of know where they are, you've thought about the ideas to put down. You tend to, I've noticed people score better. So it's kind of like a take-home format in that, there's no lockdown browser and the rest of that type of stuff. But I've watched my kids who have had to use those, and they can't move their eyes and they can't move their body. There's no way you can sit and work an engineering problem and do that. So it's kind of like a take-home, but I'm trying to fit it in the time period. I don't want to release it on Sunday because Sunday's kind of like a day for God. So I don't feel right releasing it then. And I don't want it going longer after. Because then it just chews up your whole day, and I don't know when the rest of your finals are. So I'm trying to do take-home like, but that fits in the time period of the final. If that makes sense. Any other questions? So the question that was just asked was about state tables and kind of what's going on with them and how they're set up. And my comment is that it's basically like a truth table, but we've actually altered it. So think of it, I kind of think of it as like a state table blended with a Carnot map. And this is what I mean by it. We're going to list our states. Let's say state 1 and state 0. So 2 bits. I'm going to list my states down here, right? So maybe I have 0, 0, 0, 1. I could do it in binary order, 1, 0, 1, 1. Sometimes I'll actually explicitly do this in gray code order. So you'll notice on a number of the homeworks, I said, I'm going to choose gray code to do my encoding here. And that's because it allows me to go explicitly like a Carnot map. Now, if I have to do a whole bunch of columns, like I'm analyzing it, I'll often put X here, right? Just because I need to save space going across the table. That's the whole reason for it. You know, and if you're doing like a T or a JK, you've got to calculate some intermediate things. What does the circuit say J is or T is or whatever? And so you just need room to handle that. If you don't, if it's like a D flip-flop that whatever data comes in goes in, it's then better to put X. And then since we tend to think of things more column-wise, that's why I state X equals 0 and X equals 1, just to remind us. But if you think in terms of this is basically a K-map, right? Where this is where X would be, and we usually wouldn't label that. Right? So if I put in gray code order, basically I can just look at what's here and I can see a Carnot map. And it just helps me when I'm building them. And then usually last spot, I will put whatever is the outputs over here. And very often we don't want the outputs to depend on the inputs, a Moore machine. So since it doesn't depend on the inputs, if it's a Moore machine, I can put it in its own column. And then I have a really simple output statement. You think of it as like a really simple case. And then, so then right, if I'm at 0, 0, maybe I go to 0, 1 or 1, 0, and 0, 0 goes to 1, 1, 1, 0, who knows? Maybe we're just counting through. If we go in X equals 0 and maybe I count backwards on the other one. All right, 1, 0, 1, 1, 0, 1. All right, down, up, count down, type of a thing. All right, but since it's already kind of in that K-map format, when I go to do the K-map for encirclements, right, all I have to do is go, okay, S1 is down here. That's where it's both ones. S0 is right in the middle. And X is on the top. So I've repeated this area. And I decide which bit do I want to do. Do I want to do the first bit or the second bit? Well, maybe I'll do the first bit. And I just have to copy them directly, right? 0, 1, 1, 0. 1, 0, 0, 1. And now I've got my Carnot map for a D flip-flop at least already set up. If I was doing a JK, I could then just look, it was a 0, it became a 0, and then look it up inside the excitation tables to get J and K. Right? And similarly for S0, I would just walk down the other side. You'll notice in both cases here, since I was doing count up and count down, under straight D's, you'll get this exclusive OR pattern. S0 will also give you an exclusive OR pattern. 1, 1, 0, 0, 0, 0, 1, 1. So again, you get the checkerboards, right? Just 90 degrees out of phase between them. But it essentially still gives you that pattern. And that pattern becomes much easier with a T flip-flop, but then you have to use an excitation table. And so that's sometimes with these counting ones why we do T's, right, to avoid the exclusive OR. Or I can just notice this and say, you know, oh wow, you know, this one is an exclusive OR that's based on S0 and X, and this one is one that's based on S1 and X.
Okay.
Does that make sense?
Yeah.
All right. And then for whatever Y was, I would do its own little independent thing. But since Y is only based on the states and I've only got 4, I can probably just recognize the logic function there.
Okay.
Because very often you'll get something, you know, whatever, something like that, and you go, oh, that's X NOR.
For the excitation tables, I remember you, like, for example, on the homework, when you did the same, you did like the similar thing, but
So I would recommend putting the excitation tables on your cheat sheet.
Okay.
They're in the book on, it's somewhere towards the end of chapter 5, I think. I can look it up if you want. But I also do covered in some of the videos, you know, or you can kind of deduce them. For a D flip-flop, it's trivial, so don't even record the D flip-flop ones. The JK one, which is the most useful excitation table because it's got a lot of X's in it. The way it works is, you know, this is your current state and your next state. It's only one bit because you have to do it for each bit separately. So most significant bit, you would do current most significant bit to the next most significant bit, right? What the most significant bit is going to become next, right? So this is at time t plus 1 for the same exact bit position. And so you have options, right? It was a 0, it's becoming a 0. It was a 0, it's becoming a 1. It was a 1, it's becoming a 0. It was a 1, it's becoming a 1. Right? Those are the only possible changes you could have between them. And then you just, you know, record down. You can record out of the book. The shortcut is, remember, the X's go here, and then it's a exclusive OR pattern, 0, 1, 0. So that's how I remember it. But, you know, I would say just go to the book and kind of record it down. Look at the pattern for yourself to see it and read it. And then when you're looking at any of the state tables that goes in, you know, if I've got whatever 0, 0, or state 1, state 0, X, input equals 0, input equals 1, and you'll have it goes to whatever, it goes 0, 1 on that table, right? If I was doing the one for the most significant bit for that first entry, it's a 0 becomes a 0. So that 0 becomes 0, so it's J gets a 0 in that position, and K gets an X in that position. All right, so you get 0, 1. I believe that's what I had for that column. So if I was making the J for bit 1, there's my X, sorry, S1, S0 in the middle. All right, I'd have 0 becomes a 0, well, I get J is equal to 0. 0 becomes a 1, 0 becomes a 1, J gets a 1. All right, 1 becomes a 1, J gets an X. 1 becomes a 0, right? J gets an X. And you do the same thing for the next column.
Okay.
Right? I was only able to go in straight order here because I put this in gray code order.
Okay.
Well, like I said, to make my life easy, I'll often do that.
Yeah.
Because when I'm copying, I'm dyslexic. I can copy things out of order really easily. So by forcing it into gray code order, when I'm writing it down, I have to think about it.
Okay.
And then when I'm actually going to solve it or write the rest of these, when I'm having to look up on a table and write a value down across from it, I don't want to have to think. It sounds horrible, but I don't. So
Makes it easier.
Whatever makes my life easy at that point is what I'm going to do, because I'm more likely to do it correctly. Does that make sense?
Yeah, that makes more sense now.
Yeah.
I think I got confused on the part when you were looking at like S1 and X equals 0 and then comparing it to the CS and J and then putting it on the table.
Yeah, the whole big trick is to just remember this square here is this square.
Okay.
And if I'm doing S1, I only care about the S1 bit.
Okay.
I'll do a separate thing for the S0 bit. That's a whole separate table. That's J0.
Okay.
So just ignore it right now. So I only care that S1 bit was going from 0 to 0 or 0 to 1. Right? Similar down here, just does the other column.
Okay.
If you ever get desperate and you can't remember exactly what this pattern was, you can just remember also that the JK table, remember it was 0, 0, 0, 1, 1, 0, 1, 1, and the action was hold, which means a current 0 becomes a 0, right? Or in this one, it was a reset, which means it just becomes a 0. It doesn't matter what the start was. Anything becomes a 0. This one was set. Anything becomes a 1. And this one is flip, right? Which would tell you that a 0 becomes a 1, or right? So it says 0 becomes 0, 1 becomes 1, 1 becomes 0 for this one.
Okay.
So when you're doing this, if I want to end up, right, if I'm looking at, 0 becomes 0, I could do that by this, which is 0, 0, right? But I could also do it by a reset. Any old thing becomes a 0, right?
Okay.
Either one will work for it, right? So since both of these will work, J has to be 0 for that case, but K can be anything I want.
Mm-hmm.
I'll either get this one or this one, and in either case it works.
Okay.
And for each line of these, that's what we did, right? 0 becomes a 1, right? I can go, well, here's a 0 becomes a 1, right? But I've also got any old thing becomes a 1, which would also include a 0 becoming a 1. So I could do either of these, which means J has to be 1 and K could be whatever you want.
Okay.
Right? So there's always two possibilities to walk through it. And so we just get the excitation table from here. It's just rather than have to think through this every time, it's just easier to tabulate it.
Yeah. Okay. I remember, I don't know if this still applies, so this was like before the whole COVID-19 thing. Remember the beginning of the semester, like you said, before the final, we could do like the extra, like if we felt like we were gonna miss something, or there's something we didn't feel strong on, we could like make a video over it, and then it's kind of like submit what you think you might miss before the final.
Yeah, I did give the challenge problem, but sure, I'll let you do that. I'll put up a link for it.
Okay, cool. And for
This is a good idea to do. Just think of it as a study thing and maybe helping each other.
okay,
Yeah.
for the weighting of everything, was it homework 30%, midterm is 30, and finals 40? Or what was
I
the?
don't remember. It's whatever the syllabus said. I can look the syllabus up.
Okay, I couldn't find the syllabus.
Okay, give me a sec. I'll see. All right. I found the syllabus.
Okay.
One sec here. Homework 30, midterm 30, final 40.
Okay.
So yes.
Okay.
So if you had done the challenge problem and you do this other thing, you could walk in with a safe number of points under your belt.
Okay.
Yeah. The big thing though is none of the problems are going to be designed to trick you. They're all just going to check stuff we've talked over. So, stay calm, read through them, and just give me good, solid, logical reasons why you're building stuff.
Okay.
Engineering, in most cases, is not weird trick solutions. The majority of problems that engineers have to deal with are actually usually very simple overall logic problems. The biggest issues are always reliability issues. How do you make that simple design such that nobody can break it? How do I anticipate a lightning strike or somebody randomly bapping on the keys or something else?
Yeah.
Right? Yeah. So, I don't like to get into overly complex designs because I don't think they're realistic. There are special cases, right? But really good, solid thinking is what's going to actually be the majority of your design techniques.
Okay. And for the ASCII, is the first section for the row or the column of the table?
So on the tables that I give you, the first number is the column and the second number is the row.
Okay.
So I can't guarantee every table is done that way, just the good ones.
Okay.
The first 3 bits go here and, across this way, and the next 4 go down this way. And you put a number X, 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 Y, 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 Y. Right. And then you have a leading bit that is either even or odd parity, which is determined from the others.
Okay.
Usually this is in the leading position. It can technically be in the following position. There is all kinds of little weird conventions that are out there, but I will only do the leading convention. It's the most common one that's out there. So, but just so you're aware of it, if you ever deal with it, sometimes people put things in odd spots, but it's either the front or the last. Highest chance in the front.
Okay.
Other questions? I'll pause while people think. All right, so there was a question on memory. I started to draw a picture to make sure that I understood what it was. So if you remember, this is a 2D memory here, and we had a row address, and we have a column address. We're walking through them. And usually what we do is we load the row. This is usually your most significant bits become your row. And your least significant bits usually go into the column. So the first number gets loaded into the row address. The second number that's transmitted on the bus will go into the column address. And the intersection will open up a bit. So when I look at this, this is 0, 0. So this is memory location 0. Right? So this is location 0. 0, 1, that's memory location 1. 0, 2, that's memory location 2, so on down. Right? I start the next row, right? This is 1, 0. It depends how far this goes, right? So this would go down to some, 2 to the n number of bits. So the last element would be 2 to the n minus 1. So this one would be 2 to the n. The last one here would be 0 and then 2 to the n minus 1, which is 2 to the n minus 1. So this one is one more, 2 to the n plus 1, so on and so forth. So when you loaded an address, let's say, 1, 2, this line would activate, and this line would activate, which would activate this, which is 2n plus 2, and its data would come out.
Okay.
And note, that's 1 bit. Okay? So that is kind of sequentially wise, there's my address. Now, what it will often do is we make memory byte addressable, which means the row address is the upper part, followed by the column address, followed by, inside the bits, right? So there are bits. So this is your full address to a byte. But then inside this, you have bits, right? 7 down to 0. So I'd make one of these hold 7. I'd make another whole one of these that holds 6. Okay. Another whole one that holds 5, so on and so forth.
Yeah.
Right? And then I would get each one I get all 8 bits would come out simultaneously from 8 different ones. Does that make sense?
Yeah.
Right? And that gives me a lot of parallelism.
Okay.
Right? Now, there are some cases where we do one thing fancier, and I didn't talk about this in ours because we didn't have as much time. But we'll sometimes also do an interleaving factor, where I might imagine this with 8 of these deep. And let's say I stick that on one chip. And then let's say I buy 8 chips. So I've got, basically 3 bits worth I can stick into this interleave. Right? And what I'll do is I'll make one go and then the next and then the next. I can kind of walk down it. Remember how I said this is kind of slow because when you read this data, I have to amplify it and all kinds of other stuff. I can be looking up each one of these in parallel to get that group of 8. Right? So that I'll pay the access time for one, but I'll actually get, 8 different bytes simultaneously.
Okay.
I'll be able to shove them out really, really fast. Because since I can't make these slower memories quicker or too much quicker, I'm limited by the devices that are there. And I don't want to make them, I don't want to put fancier devices. They take more room and they take more power and they put more heat out and all kinds of stuff like that. So I'm stuck with these slow devices. So how do I make them fast? Well, I put a ton of them that act in parallel. Right? Yep. If you've got slow devices, and that's what the interleaving is. You basically just get a whole bunch of these that work simultaneously, and we just try to increase more and more what that simultaneity is. That's the whole trick with interleaving. I didn't put it in here just because time-wise, they're just, with everything else we were doing, I want to make sure people understood the basic design factors. And this really is just to help you understand. We talk about this really heavy in detail in comp.org. But if you kind of understand physically where it comes from, in comp.org, when you deal with this, and they'll talk about burst modes and interleaving factors and stuff like that. All they're really telling you is how they're going between these, and you get a group of different ones, and you just put them in order. So you're parallelizing individual bytes.
Okay.
Does that make sense?
Yeah.
All right. So don't worry about, a lot of this is really just, we've got the hardware understanding now, and I wanted to kind of lay the ground for the next class.
Okay.
I suppose I could ask a question about it, but I'd say I'm 99.9% likely not to.
Okay.
Just because it's not as much of a problem for me. It's really more of your next class.
Mm-hmm.
I do want you to have seen it before, so when you see it then, it's just like, oh, I remember that, and it's a recollection problem.
Yeah.
Not a problem of you're trying to digest all of their stuff and then figure out the hardware too.
Okay.
But there's not a lot of question you can ask on this other than, how many addressing bits and, where is this byte located? And they'll do all those type of problems. So I don't feel the need.
Okay.
Did that cover what you needed?
Yeah, thank you.
Awesome. Any other questions?
I think that's everything.
Awesome. So like I said, I'll make a WebEx chat simultaneous with the final for people to ask questions. I'll put a bunch of the kind of the notes we said on how the final will play out as an announcement. So you'll kind of have a written form of it. And then this, it's, saying we've got about an hour and 17 minutes have gone by.
Mm-hmm.
So I would imagine it'll probably be ready in like about 10 hours, knowing WebEx.
Okay.
So as soon as I get it, I'll post this video too.
Okay. Sweet.
You can also find it by looking under the, if you go to WebEx, the kind of event tab, 2 over is the recordings.
Uh-huh.
So you can check too, because I have to notice it and then download it and then re-upload it and then check that it uploaded correctly because it hasn't a couple times, and then make it public and then post it on a page. So probably takes me about an extra hour or two beyond when it's first available.
Okay. Okay. Well, thank you so much.
You are very welcome. I hope you have a great day and a weekend. And see you on Monday.
All right. See you.
Okay. Bye.